let's recall Hooke's law. Applied to spring or other elastic object when we apply force and we encounter resistance due to elasticity either of the spring or rubber band or something like that. So Hooke's law said that the force that required to either stretch or compress a spring is linear with the displacement. So in short, it would be like that, where K is the constant. So, and here was the example that we started last time and will continue today. So the force, a force of 40 Newton is required to stretch a spring from its natural position of 10 centimeters. Natural, actually, instead of position, I say length. Because we're talking about a spring after all, so of 10 centimeter to a length of 15 centimeters. This part was given last time. Okay. So when the spring is relaxed, it has a length of 10 centimeters. When we pull on it or stretch it with 40 Newton, it stretched to a length of 15 centimeters. And the question is, how much work is done when we stretch the spring to 18 centimeters? This is centimeters, kind of squeeze it at the end of the line. I'll write it here. So this is a two-part question. Really, the first part, we'll use the information that we have that a force of 40 Newton is required to stretch the spring from 10 to 15 to figure out what is the constant. So we're going to say the following. F of x is k times x, okay? And we know it's equals 40 Newton when the displacement, I'm talking about one end of the spring is displaced by 5 centimeters, the difference between 10 and 15. So the displacement is 5 centimeters, but since we are dealing with Newton or with the metric system, we need to write it as meters, so 0.05 meters. And so we solve for K. We're going to set it up, F is 40 equal K times 0.05, and from here we get the constant, which is 40 divided by 0.05, and this amounts to 800, and the units will be the force on top and the displacement at the bottom, so Newton over meter, like so. Okay. So this was the first part. So now we applying k into our Hooke's law, and f as a function of x is simply 800x. Again, x is the displacement, is by how much we move or we stretch from the natural length of 10 centimeters. All right? So what is the overall work? Well, by how much we're going to change? Delta W will be the work done. W is, in general, it will be f of x dx, like so. And so it will be the integral 800x dx. And the trick part is, well, let's write the general term. It will be from x1 to x2. Specifically, what is x1 and what is x2? We want to know how much work is done. We stretch it from, let's say, 15 centimeters to 18 centimeters. So the initial position will be what? Is it going to be 0.15 to 0.18? What is the displacement originally? We need to go, what I said is incorrect, because we need to go from the natural length. So 15 centimeters is 5 centimeters off the natural length. So x1 will be 0.05. And x2 will be 0.18 minus 0.10, so x2 will be 0.08. I'm sorry? The natural is 10, 18 centimeters minus 10 is 8 centimeters. 8 centimeters is 0.08. Meters. The natural length is 10 centimeters. Remember, our units are Newton per meter, so. I'm sorry, one person at a time. Let's, lady first. Right. But we already, the question is, well, how much work is to further stretch it from 15 to 18, if it wasn't clear? So the initial position will be 15 centimeters, which is 5 centimeters off the natural length. So 0.05 will be the one boundary of the integration. And then we stretch it to 18 centimeters, which is 8 centimeters or 0.08 meters from the natural length. Okay, did I answer the other two questions that there? There were 3 people asked at the same time. I answered, I think there was a question from the far wall. Did I answer your question? There was also somebody from this area. So you're all clear? Why the boundaries? Other than the setting up the boundaries, which is the tricky part, everything is straightforward. So the idea is, whatever you do, x is measured from the natural position. Well, the result of it is, of course, 800 times x squared over 2, evaluated from 0.05 to 0.08, and the answer is 1.56 joule. Joule, because again, we are dealing with metric unit. Okay? So where is the difficulty here? Again, where x, note here at the very bottom of the page, x equal displacement from the natural length. This is something you want to keep in mind. And this is true, and you'll see in the following 2 examples, this is not only true for Hooke's law, spring, and it's pretty much the same for all work problems. You need to consider what is the displacement, not what is the actual value of the position. The position is always measured from a reference point. That would be our x equals 0. But we start to work when the object can be 10 meters away or 15 centimeters away or half a mile away from our reference point. So we go from there, we move with a certain displacement, we go from the initial position to the final position. That is the displacement, okay, regardless of the reference. So we don't go from 0. Make sense? On to the next example.